Chapter 6 is going to be about electricity. We're going to cover the Amber effect, electrons, protons, neutrons, electric charge, electric force, electrostatic charge, measuring electric charge and force, electric fields, electric current, resistance, AC/DC, electric circuits, voltage, Ohm's law, electric power and work, and then magnetism. So electricity was a mystery for thousands of years. We didn't really understand what was going on, and it really all started with pieces of amber. No one could figure out why a rubbed piece of amber would attract other pieces of paper, thread, and hair. So you can see here there's the amber image on the left, and then you have what we see here is a cat who's completely covered in packing peanuts, so that's kind of similar to the relationship that they observe between amber and rabbit's fur or pieces of paper or thread, how it would essentially cling to the material. And so you can see here there's amber, the cloth, the two are rubbed against each other, and all of a sudden now that piece of amber is charged and able to attract pieces of paper, thread, hair, and fabric. So about 100 years ago, J.J. Thomson discovered that all matter contained negatively charged particles. So that's still a relatively new discovery to us. The Greek word for amber was electrons. And so that's where the word electron came from to describe these negatively charged particles, is from the Greek word for amber. And electricity is also derived from the word amber. So here you can see we have a picture of an atom. You have the neutrons and the protons that are inside the nucleus of the atom. And then on the outside we have, in these rings, electrons that exist in shells. And so J.J. Thomson contributed to the discovery of the electron, which was really what we need to understand in order to know more about electricity. So electric charge is something that all electrons and protons have. It's what we call an inherent property, meaning it cannot be separated. It's part of it. It's ingrained. And it's also a fundamental property that we talked about. Electrons are negative. Protons are positive. So I try to remember this by thinking of the T in protons as the T in positive, or you could think of the P and the P. And then electrons are negative. So I try to keep those two letters together. And then the neutrons at the very center, these are considered neutral. So they don't carry a charge. Now most all of our elements that are on, well, all of the elements that are on the periodic table are going to have an equal number of electrons and an equal number of protons. And that's because the charges are going to cancel each other out. But for the most part, the number of protons and neutrons are going to be what contributes to the mass of the atom we're going to see. But they're not always necessarily equal, like we see here in carbon. The only two that are going to be equal to each other are electrons and protons. When electrons and protons are not equal, we're going to have what's called an ion that'll form. So the electric force is when electric charges interact. So a proton and a neutron, a proton, an electron. But they're going to interact in some way, and they'll produce a force, which, just like in Chapter 2, it's a force that can be used to do something. The general rule is that like charges will repel, and unlike or opposite charges attract. So here we have two protons that are side by side, and they are repelling each other. You can tell that they're repelling, the arrows tell you that, but also there's this space between them when they're not interacting at all. Electrons, when they're near each other, will behave the same way. The only time that we're going to have two charges attracted to each other is when they're opposite charges and the force is pointed towards each other. Okay, and that will bring the two charges closer together. Now, electrostatic charge happens because electrons can be moved from one atom to another atom to create ions. So here we have sodium and chlorine. They're two elements on the periodic table. And we can see that the arrow here represents that sodium loses an electron to chlorine, who gains that electron. So when electrons are gained by something like chlorine, they are gaining something negative, and they're going to become negative. And that's what this minus sign right here represents, is now chlorine is negative. We're going to call these negative ions anions. They are negative. When something like sodium loses an electron, it's going to become positive, which we see here. And we're going to call these cations. So always think of the T in cation represents the positive sign. The N in anion represents negative. Okay, so these two, through the loss of an electron and the gain of an electron to chlorine, are going to form ions. So it's where the electrons and the protons are no longer equal to each other. We have an imbalance. The easiest way to remember it is if you gain something negative in your life, a negative friend, a negative workplace, negative anything, your life is going to become negative. If you stop hanging out with a friend, if you quit that negative job, your life should become more positive. And that's the same thing with the gain and loss of an electron. Another thing with electrostatic charge is that we see that electric charges on objects result from the gain or loss of an electron. So just like sodium and chlorine can gain or lose an electron, objects can gain and lose electrons. And when that happens, we have what's called electrostatic charge. So because the electric charge is confined to an object and it's not moving, it's called an electrostatic charge or static electricity. So we see here we have a comb and the hair, and in the beginning, before they touch, there is no net charge, meaning that there's 3 positives and 3 negatives on each of these, the brush and the hair. Once the comb comes through the hair, the negative charges hop over to the brush, and now there are 1, 2, 3, 4, 5 negative charges on the brush and only 1 on the hair. So that's imbalanced. And then what will happen is the hair, as we see here, will become staticky. So that's what static electricity originates from. It's also going to be similar to what we see with lightning whenever we get to weather. So how do we measure electric charge and force? Well, electric charge, we're going to give a symbol of capital Q. Sometimes it's also lowercase q. I'm not sure why it's interchangeably used that way, but capital Q and lowercase q are going to refer to electric charge. And they're going to be measured in units of coulombs. It was one of our fundamental units we talked about, one of our 4 fundamental units. The charge of 1 electron is the fundamental charge. So that value is 1 electron is equal to 1.60 times 10 to the negative 19th coulomb. Protons are also 1.60 times 10 to the negative 19th coulomb. They're equal and opposite, and that's the charge of 1 electron. So what happens is, what is a tiny shock versus a huge shock? Well, here you can see this looks like major shock. Well, major shock occurs when you have a lot of electrons. Okay, a lot of electrons flowing at the same time. A small shock, like if you touched a metal doorknob or, your static electricity in your hair, that's just a little bit of electrons. You can kind of feel it. It might feel like a zap when you touch it, but it doesn't electrocute you. Okay, so the more electrons that are in the object, the more shock we feel. So electric force, on the other hand, is described by Coulomb's law. Coulomb's law tells us that there's a relationship between force, the distance between the objects, and their charges. Now this is a constant that we're not really going to worry about because it's always going to be the same. It doesn't matter what the charges are, doesn't matter how far apart they are, K is a constant, so it's really not something we have to concern ourselves with. Now, when we have a force of attraction, we know it's going to occur between unlike charges, right? So when this is a positive and this is a negative. When the force is repulsive, it's going to be because the charges are like each other, 2 positives, 2 negatives. The one variable that's kind of new to us is what R means. And R is going to be the distance between these charges. So the closer we bring 2 charges together that are feeling attraction, The closer we bring them together, the stronger the force is going to be until eventually the two charges smack together. So as we take the charges further apart, at first it's going to be really hard to get the charges apart, but eventually they're going to be so far apart that they don't feel a very strong force between them. The same thing occurs between like charges. If I take a positive and a positive charge and I start to bring them together, I might be able to bring them close to each other until a certain point, and then the repelling force between them is going to be so great that I'm not going to be able to get the charges any closer together. So the force will increase as we get the objects together, closer together. Whether or not that force is attraction or repulsion depends on the two types of charges I have. So another thing that happens when we have two charges is what's called an electric field. Very similar to the term force field, but because it's electricity, it's going to be an electric field. So when two charges are close together, doesn't matter which two they are, a model is going to be used to describe the space between the charges, and that model is called an electric field. When I have a positive and a negative, we said this is when we're going to have attraction. The lines are going to point from the direction of the positive to the negative. And that's going to happen with the lines that are in between the two charges. You can see here the force field lines come in. Over here the force field lines are pointing out. The closer the lines are together, the stronger the field is. So when they get further apart, these are not as strong. So these are weaker areas and these are stronger areas. When the charges are the same, meaning two positives or it could be two negatives, we're going to have a force field that's going to indicate repulsion. So in this case, you can see the lines are still going to point away from the positives, but there's going to be an area where there's no interaction at all, and it's almost like a void. And this is where once we get to a certain distance or radius, we're not going to be able to get the atoms, the ions, any closer together because that repulsion force is going to be so strong. So these are the electric fields for an attraction, and repulsion situation. So we're going to take a break and come back to finish the next part of chapter 6.